Welcome to the CSOI Student Brown Bag discussion. This week we have Yao Zhu from the Center for Science of Information. He's a PhD student in the Computer Science Department. He's going to be presenting on learning the building blocks of crystal structures. So we're going to give it a run here, and with that I'll turn it over to you, Yao.
Okay, thanks. Thanks. My name is Yao Zhu. I'm a fourth year PhD student in Computer Science Department. I'm working with Dr. Alan Chi on machine learning, especially probabilistic modeling and approximate inference, and using these techniques to solve real-world problems arising in biology, psychology, and as well as material engineering. So we care about the crystal structures, but we care what are the essential substructures that we can use to compose crystal structure. So this is based on a collaborative project with material scientists. So first I'll go through the motivation and background of studying crystal structure, and then we'll pose the problem. What do we mean by learning building blocks of crystal structure? And then how we are currently formulating this problem as a constraint co-clustering mathematical problem, and how we're going to solve this problem use some technique called joint affinity propagation. I'm going to explain this later, and we'll show some demos on toy examples, and we'll discuss what are the questions we need to solve along this line. So material scientists, engineers, they care about crystal structure. It's because the knowledge of crystal structure help them to understand the properties of materials, as well as make them to be able to develop materials with specified properties. You can consider the information of crystal structure to be the initial value condition for solving a partial differential equations. So this knowledge is really the starting point for further calculation-based or simulation-based research. So here you can see, okay, the crystal structure is nothing but the three-dimensional configuration of atoms or ions along the lattices. You can see that here's a one dimension, these polyhedrons packed together, and this is another dimension, and with three-dimensional, this is another dimension. Okay? So there are several ways to predict or understand the crystal structure. The first, of course, is through chemical experiments, but it's very expensive. It takes a lot of time and human labor to conduct chemical experiments, and still you need to understand the experimental data later. And the second approach people from material science they try is from the energy minimization, which I call first principle calculations. This is totally based on statistical physics, and you try to minimize the energy of the structure, and you consider the structure achieving minimal energy is the presumable structure for the material. But this is still very, very expensive because this is NP hard, or even more than NP hard problem, because there is too many freedoms of configuring the atoms. The third approach is recent years by the increasing computation power, people consider, say, if I already know some crystal structures, then we follow a data-driven approach. So this is what we really care. So we try to use data mining techniques to help us predict the crystal structures of materials we don't know the structures. So, but however, this is not a new idea. There's some people already did some work along this data-driven approach. What they did is they say they know the compositions of the compounds or materials. Okay, so for example, you have 1 calcium and 3 oxygen and 1 Ti. Using this composition, you have a crystal structure. So they say, okay, suppose from the periodic table, I know that calcium and this Ba element are in the same column. It means they belong to the same family of chemical elements. So they're very chemically similar. So they say, okay, if the composition is preserved, this compound has the same composition of 3 elements of this compound, and these two elements are very similar. They say, okay, we can use some statistical techniques to compute the correlation of the composition with the structures we know, as well as by taking into account the similarity between elements. Then they make some prediction of the structures of this composition. And this is also follows the same idea. The only thing is these 2 elements are similar.
So I'm saying that if you know a structure of some crystal and you have a new one, you can basically, the new one, you can somehow fit into database of known structure to learn the structure of the new one?
That's what they doing. They say, okay, I for these compositions, like the 131, this is 311, then okay, for this I know the structures with, and this is the same composition of this, and they are even follow the same chemical class in the same chemical family, then they should be very similar. But this is assumption, and this does not get you out of the known crystal structures. You restrict yourself to the closed world of crystal structures. So this is not the approach we are following. We follow another approach, more structural. Say, the idea is that, say, I know this is a crystal structure and it can be represented as a graph or even weighted graph of nodes and edges. And if you look at this, people already know this crystal structure can be decomposed as 2 building blocks. The first is octahedron, the second is tetrahedron. And you just pack these 2 building blocks in some densest way. Okay? So densest packing is a traditional problem in statistical mechanics. But they are using, say, they're using a given set of building blocks like octahedron and tetrahedron. These are all platonic solids, and there is a paper published, say, how I'm going to use energy minimization technique to pack these building blocks. What we are doing here is the inverse problem of this. We'll say we're given a big graph or a database of crystal structures. We try to cut it into essential subgraphs that we think are meaningful in representing the big graph. So this is what we're doing is the inverse problem of this traditional densest packing. So the idea is that by decomposing the already known structures into these substructures which we think to be preserved across different crystal structure, we're going to be able to use these building blocks to compose the new crystal structure of a given material. Hello?
Don't worry.
Hello.
Don't worry, they are just joining us.
Okay. So before we go on, let's first do a survey. Suppose I give you this this graph, fully connected, with different weights on the edges. I ask you to cut it into 2 pieces. How are you going to cut it?
What's the criteria? What do you want to get?
I only tell you, okay, to cut it into 2 pieces. Now you are given 1 piece. I want you to cut it in 2 building blocks. Say these 2 building blocks are connected to form this graph, and you only know the weights. You know the weights on the edges. They may not be the same. For example, these 3 edges may be with weights larger than other edges.
I don't understand the question.
So in terms of what? I mean, you have the same. I mean, the two groups have the same weights, or?
It's not necessary. It's saying you just I have weights on these edges.
Yeah.
Right. In a spectral clustering, you can cluster according to the edge weights. I just ask you to cluster it into 2 groups of vertices.
And what's the criteria? Any cut or
Yeah.
The criterion could be the though you want to cut it in two groups, and within one group, within each group, the connection weights are larger than other cutting weights. That could be a criterion, right? But this is still too symmetric, right? You can cut this way, you can cut this way, you can cut this way. Maybe the total sum of weights are almost the same. So it's hard if we only know the connection weights. But how about this? I color the nodes. For example, I say, okay, these two nodes are chemically similar, or they are just the same elements, and these two green nodes are the same elements, and the two blue nodes are the same elements. Then I still ask you to cut it into two pieces. Then how are you going to cut it?
What's the constraint?
What's
the constraint in cutting?
The constraint is just that you just want to cut them into two pieces in the way you consider to be making most sense out of it. Right? In the crystal structure cutting problem, you're given this crystal structure. Nobody can tell you what will be the best criterion to cut it, because nobody knows what should be the meaningful building blocks. So it's totally exploration problem. Right? We try to make some symmetry and objective into this. So just like this example, this crystal structure considered, and I know the elements on the nodes, and I may have some knowledge of the weights on the edges. Then how are you going to cut it?
So if I understand the question correctly, you're trying to cut it into two building blocks so that you can say this crystal is composed of two building blocks.
Right. But say, for example, somehow you can cut it here, because then you consider this. If I cut it here, then I have two triangles. Then the rest is nothing but connecting the triangle vertices. Right? You have several ways to cut it into two pieces of triangles. One is that you have another way like this. Cut it this way, and the rest of this way. And this way.
Could you repeat the question, please?
His question is, given this structure, what I'm doing is try to cut this structure into two building blocks, and what would be the criterion? Right?
The point that's not clear to me is why are you going for two building blocks? So why not three? Why not four?
Right, that's a good question, but that's also the freedom we need to explore. You may say, I just decompose it into edges, but that's another choice. For example, you may decompose it into the edges of the same color, but this may be over-cutting. So the size constraints on the building blocks is a problem we're looking at. So there are a lot of freedoms, and one way to me that makes sense to cut this one is to cut this into two triangles with their colors, with three different colors. Because when you cut this way, or either this way, or either this way, you have two triangles with their vertices that can be aligned according to the color. So it means that this building blocks is really preserved in this crystal structure.
Even for triangles, you have two choices, right?
Right, okay, this is the one way, right? I mean, triangles with the vertices of three different colors. Right, you may cut it into triangles with two colors, like this and this one. But this is not very symmetric. They do not align with each other. Right? They do not enforce their appearance in this structure.
Let me make my question clear. So you have two kinds of cuts here. One case you are considering the cut to be along a rectangle. So along the edges of a rectangle, like the horizontal line there.
This one or this one or this one.
Oh, you're saying they're all the same. So from the drawing, it doesn't appear so.
Yeah, to me, okay. If you don't know the weights on this, it seems that the three different ways to cut it are almost the same. They produce two triangles with three different colors, where the colors can be aligned. But if you have weights on the edges, this one saying you have another knowledge. You not only know the colors, but you also know the weights on the edges. You want to make sure the cut two pieces have the weights within the building block, within one building block to be maximized. So you have these two information. One, you want to align the nodes of the cut building blocks, and you also want to preserve their connections as much as possible. Right? Without this color, you may have several ways that achieve the same weights of connections. But with this color, it may reduce the ambiguity in this cutting. So I should put some weights on here, then it will be more clear. For example, this is 1, 1, 1, and this is 1, 1, 1, and these are 0.5, 0.7. That will be very clear, then you just cut this way.
Does the weight, do the weight actually in this graph actually, the length of the edges actually represents their weight?
No, I just draw it not according to the length. I did not draw it in the, yeah.
So actually you want to find just like a min cut plus something, plus some other constraints.
Right. It's pretty similar to say like a min cut problem, but at the same time you want this node to be aligned.
You mean so in this example, so for each group we should have 3 different colors, right?
Right. Because this is the only way to have every vertex as a pair in the second triangle.
Yeah.
Otherwise they will not align with each
So
other.
the some noise.
Yeah.
So it's kind of like a min cut plus
The
this
node,
constant, right?
node alignment
Depends
constraint.
on the audio
Yeah.
conference. I'm gonna turn that
So the color really matters. With this color, the knowledge of color, we have reduced the way we cut this. So we reduce our search space. So then let's see what's the real input of our problem. In our problem, we have ions, and we know that can be used to form crystal structures, materials. We have the charges. This is and this table tells me that whether two ions are similar or not. The larger this value, the larger the similarity. For example, this zinc is similar to this CO when they are both of 2 positive 2 charges. And this is some data that from our collaborator. They conducted this statistical analysis to extract this information from the known crystal structures. And the second input is the crystal structure graph representation. And we have a database of crystal structures. We can consider, we put all these crystal structures as one giant, big, very, very big graph. So given these two sources,
And what is the last column? The color A?
we have 3 columns. The first column is the element identity, the charge, 1 and 2 different ions. This column measures how similar these 2 ions are when they form crystal structures. Okay. And we have the graph representation of crystal structures. It could be very, very big graph. We put a lot of crystal structures together as a one giant graph.
So how similar they are when they are close to each other? Yes. What do you mean similar? In what
This
sense?
one, okay. This
Chemical similarities.
similarity could consider this kind of factors. The first is the charge is similar. Okay. In this case, in our study we will discard this row because they have different charges. It will affect the radius of the ion in the space. First is the charge that were similar. Second is they made from the same class of elements in the periodic table. The chemical probably is similar. And and also we consider some, this is based on the physical and chemical knowledge that provide this table to us. So it's also, this also open-end, we can try different ways to measure the similarity and see how it's going to affect the cutting process of this big graph. Okay, but suppose we're given this input, and we are also given this graph, and because it's crystal structure, we know in each vertex what is the ion identity of that one. So these two red nodes does not necessarily mean they are of the same ion, but they could be just quite similar according to this table. So we have this color graph or labeled graph, and we also have the weights on the edges. These weights are extracted from the crystal structure because of the atoms are close to each other or far away from each other. So that's the weights.
Excuse me. So what are the weights? Is not on the left hand side, or
the weights here is not on. This is not the weights here, because this only tells you the label, the vertex. The vertex, the number of vertices could be much larger than the alphabet of ions. Right? This is just tell you whether two ions are similar or not. The weights here are extracted from the crystal structure, okay, where two atoms are very close in the space when they pack together, or they are quite far away, although we consider there's an edge connecting them. Okay, this is also defined by our collaborator. They consider that way to represent the crystal structure as a weighted graph to be the most meaningful to them.
so can I see that? Can I just consider like this? So the left hand side is actually be used to determine the color of the graph on the right hand side. Right. I mean the red ones.
So okay, you say whether this is used to color the graph.
Yeah.
Almost right. The only difference is that when we color this graph, we just color it as the ion identity we know from structure. For example, I have a crystal structure of FeO3, and I know the atom, which elements are Fe elements, which elements are O elements. So we color it in that way. But that color, we also consider these two labeled nodes. If we look at this identity and this identity, we look back into this table, we find whether they are similar or not. So this, I just color this way, say these two nodes, where they know their identity, you look back in this table, they're quite similar, so they are colored the same color here. Right, so there's like a dictionary lookup process.
So there should be a threshold over there, right?
We don't take in, because in our algorithm you can see that we don't need a threshold. We just try to maximize some objective function.
Yeah. I mean, to decide the colors, you need to give a threshold, because you look up, for example, these two red nodes.
Okay.
So you look up the table. If they are, the value is large, you actually assign them to the same color, right?
Right. So you're saying that whether we first determine the color based on this table and then do the cutting process.
Yes.
Okay, this is one way to go, but we're doing another way. We just say we just know the node identity, and we do the coloring as well as the cutting jointly.
Oh, simultaneously.
Yeah, simultaneously. Optimize the objective function. Okay, we'll see the objective function later.
Yeah, I have a naive question. So, if you have chromium 6+ ions and sulfur 6+ ions anywhere in the cell, you will color it with the same color?
No. The coloring is not predefined. The color, I just show you this color just to tell you the intended cutting will be into two tetrahedron with this node aligned with this node, this node aligned with this node, this node aligned with this node. This is for this color is not the input, is what we try to learn.
So what is the connection between the left table and the right? That's the part I'm not seeing. So
Okay,
They're two separate illustrations. They're not necessarily directly linked. Yeah, I can spot everybody's getting confused. Sorry, yeah, am I correct?
Right.
Yeah, sorry.
So this is just help you to determine the color along the process when you cut the edges. So with these two forces, one is you try to cut the edges, one is you try to align the nodes. So in the end, you get these building blocks which you think make sense. Preserve the edge connection, also with the nodes aligned according to this table as well as possible.
It's kind of like a co-clustering, right? Because you actually have two graphs here.
Right. That's why in my outline, I really say it's a constraint co-clustering process. But when it's constraint, I will tell you what's the constraint. Yeah. Okay, so before we go to the our formulation, we consider the two related problems to this problem we are studying. The first is frequent graph pattern mining. Okay, so this is we really try to understand to learn the substructures, subgraphs from the big giant graph, and we hope that the frequently appear subgraphs to be captured. So this is why this is related to this. But however, it's a big difference is that in this approach, in this research, people say once I fix the labels of the nodes, I do not consider their similarity between the labels of the nodes. Like for example, I have two nodes, they're labeled by FE and ZN, then they consider them to be two different labels. They don't consider whether these two vertices labeled differently to be able to be aligned together. So they have this kind of similarity concept. And another difference that we don't really care about the structures which appear a lot but does not necessarily make sense. For example, the edges could appear a lot of times. We don't want these kind of graph patterns to be captured.
Why?
That's because we just try to learn a set of building blocks which is capable to describe the structure, but not necessarily redundant.
So I think what you are saying is the following. Let's explain on the pattern matching, which is much easier. When you have a sequence, you have a long sequence of DNA, and you have a small pattern, and you want to know whether this pattern is relevant or not, instead of pattern things about small graph. So you are counting how many times this occurs in a long sequence.
Right.
And based on this count, you have to decide whether the pattern, this occurrence, is relevant or not statistically. So what you do? One way to do it, you compare to probabilistic model. And if you can generate that many of occurrences in a probabilistic model, obviously it is irrelevant. Right. Because random things can generate. So what you have to do from frequent graph pattern mining, you have to discuss the following problem. There is a paper by Shabbat who actually does it very nicely. So you have a graph and you are looking for subgraph, how many times it occurs. So she actually designed a probabilistic model, and she tells you, if you have a triangle, this triangle should occur on average 25 times plus minus dispersion. So if you have actually 30 times occurrence, you say this is normal behavior. There is nothing interesting there. But if you have 5 occurrences or 500 occurrences, you know that the probability that this occur randomly is so small that this is actually statistically significant, and you can actually do it. So that's what they do there, I believe. So the age, if it occurs, let's say you know how many times typically it would occur, and if it occurs much less or much more, then eventually interesting. So it's not about age; it's about actually structure and how many times it occurs in a typical graph. That's what I think it is.
Right. It's this kind of randomized test could really be used to assess our algorithm, whether the algorithm really extracts something interesting or just sporadic, just by chance did it extract that structure. Right. Because we really have big headache of how to evaluate the learned building blocks at this moment. Right. On this toy example, I can design it what you say. Yeah, thanks. The second problem is graph alignment. The graph alignment is it's just try to align the two graphs along the nodes, as well as preserving the edges with the between the aligned nodes. So this our problem also has some elements of this alignment, but they are still different problems from us. Okay, so we formulate our problem as a constraint co-clustering problem. So there are two clusterings. So we say it's co-clustering, and I will describe what the constraint means. So if I look at this graph, I know these two nodes are similar. These two nodes are similar. I know this knowledge, and I know the graph connections of this node of the vertices. So I want to cluster it first according to the node's identity. For example, I want to cluster these two nodes in one node cluster. I want to cluster these two nodes in one node cluster. So I have 4 node clusters. That's by looking at this graph, what was the intended solution. And another dimension to the clustering is just looking at the weights on the edges. You want to cluster the nodes into 2 or 3, or there are a lot of freedom here. You just want to cluster them into edge clusters so that each edge cluster, the graph connections are large, not small. Okay.
How to make sure that because in clustering we know that we cannot make sure, so for each cluster we have like 4 elements or 3 elements. We cannot decide that how to ensure the balances between clusters.
Okay, right. Your question is how do we how do we enforce the clusters are almost of the same size?
Right. Because you mentioned that each building block should contain, like say, in the previous example, should contain 3 colors, right?
In that case, it's because only it has 3. First, only the building block has 3 vertices. They could have 3 colors, but it's still not definite. Even 3 vertices could have 2 colors in that graph, right? So right, so this kind somehow we're using the node to guide the node identity. So why this is combined together? This is because the node identity can guide the decomposition of.
Yes, but it cannot help. But it cannot do. But it cannot make sure that the clusters are balanced. Right?
That's another constraint we can add to this co-clustering. This is not you're saying the constraint. One constraint is the size constraint. That's something we can extend our algorithm very easily. I will show you. This is the constraint algorithm we're using is affinity based on affinity propagation. The nice thing of affinity propagation is that you can add constraints to it as you want. Okay, well, I will tell you why that's true. Somehow, really, we want to balance the size or put some constraints on the size of the clusters, but we don't know how large or how small a building block could be. So that's the freedom we need to explore this. So the 2 clusterings along the node identity along the graph, and how to put them together, that's the question we try to solve mathematically. So this constraint, then I need to state the constraint. So if you look at this structure, I see these 2 red nodes are aligned in one node cluster. Then I don't hope them to be within the same edge cluster or within the same subgraph. Why? Because in the end, when you want to learn these building blocks, you have a lot of building blocks. For example, you have tetrahedrons like this. You can learn a lot of tetrahedrons with different identity on the nodes. And the thing you want to see is that I know these 2 nodes are aligned this is not a graph edge. This let me go another way. So if I know these two nodes are chemically similar, I know these two nodes are chemically similar. I know these two nodes are chemically similar, and these two nodes. I want to have this alignments of nodes to be occur within different subgraphs. If you tell me, okay, these two nodes in the same graph are also node aligned because of their chemical similarity, it's not very useful for me because I treat this whole as a building block. I want to know is whether this node is aligned with this node. So if this alignment occurs, then we know this building block, we can abstract it a little bit of the element identity on the nodes. So that's where it's useful for us. But if you tell me these two nodes align, but if they're in the same subgraph, in the cut subgraph, this is not useful for us. So that is the constraint. Let me state it out. The constraint is if I have node I and node J, okay, that's just like two nodes or two nodes, indices into the nodes, they're clustered into one edge cluster. First, that is the connected component or subgraph. Then they should not be clustered into one node cluster. So that's our constraint, because we want the building blocks to be useful.
Is that too hard? Is this constraint too hard?
This constraint could be incorporated into the affinity propagation framework.
Yeah.
Okay, if you mean hard, say this is NP hard to optimize because of this constraint.
I mean, it's too strong, this assumption.
This assumption is not, I think it's not very strong. It's because just from the utility of the building blocks, we are not interested in you tell me these two nodes are aligned.
Suppose so here you have 8 nodes here. Suppose you have the 9th node. So where will
okay? So what you mean you have another node?
Yeah, nice.
This another node maybe occur in another graph. This is not nice node you call this.
Just a single. Just a single.
Just single node.
Yeah.
I claim that our algorithm will not produce a single node. Our algorithm won't produce a single node.
Okay.
Why? Because if we want to maximize some object function,
yeah.
Okay. Well, I haven't shown you the object function. The object function is really considering the edge connections of subgraph as well as the node alignments along different subgraphs. If this node, if you, in the input graph you have these singletons, I can totally discard them because they do not have any structural information, right? It means that this node must be connected to some node in the input graph.
I mean, connect to some cluster. That's one of the two clusters here.
I mean, connect.
I mean, suppose you have nice node. Which cluster would you put this node in?
Oh, you mean these two clusters? Which this one will goes to?
Yes. That's why.
This determined by my algorithm. Right? You cannot say my algorithm output a singleton node and you ask me which one it goes to.
No, I don't mean that your algorithm will give a cluster with only one node. But I mean, if your algorithm gives only 2 clusters and you have 9 nodes here, so which cluster this single node will goes to?
That depends on the.
So that's why I said this constraint.
If this node could, okay, this constraint does not necessarily mean that 2 clusters are of the same size. Are you?
I don't mean that they should be the same size. I mean that probably in one cluster, probably 2 nodes may share the same node similarity.
Right, but we just don't learn that, right? We just discard that. When we cut the pieces, we don't look into. When you cut, you have 2 parts. You have the edge, you have the node. When this algorithm runs, you really have the partial information of what should be the affinity that nodes prefer to be in one subgraph. That information will affect to how the node choose the aligned nodes in other subgraphs.
Okay.
So that way, it's really it's not say this. Suppose this node also, in the end, it's linked in this cluster. They have 5 nodes here. This is the big cluster. It could also be, say, I also align with this node in node similarity. It's also allowed. So that's the post-processing. I think you are asking the problem. Say, if I learn this cluster, and align this way, there's not one-to-one correspondence.
We have only 4 colors.
Why 4 colors?
Yeah.
I can't have any number of colors. The colors are defined by the alphabet of the ions.
Oh, I see.
Right. I'm not saying I define the number of colors. If this is Fe, this is Zn. I just say Fe and Zn in my similarity table. They are very similar. So I align them together or cluster them together. Right. So how are we going to mathematically describe this co-constraint on and solve it? So the algorithm we're using is called joint affinity propagation. So usually when you see joint, it means this work is the old work. Some people did it already, then we just put joint and we produce new algorithm. So first we'll look at affinity propagation, and the affinity propagation is you give me a similarity matrix of n objects. We have n objects, the similarity matrix is n by n, and from this similarity matrix, you tell me what objects could be considered as exemplars such that the rest of the objects could cluster into. Let's look at a picture that'll be clear. Click here. Okay, this is the video. Just show this. So you have these nodes in the 2-dimensional space. Okay, and the similarity is provided in a matrix. It's not provided in a metric function form. So it's a non-parametric constraint. It's not like a k-means that you have the distance defined and you try to find the centers, which in that sense they are parametric. In this sense, you just give me an n by n similarity matrix, hopefully positive or non-negative, and just want me to show what should be the exemplars. So let's see a run of this.
You mean your algorithm is non-parametric?
Right. Affinity propagation is non-parametric.
Okay.
So you can see as the iteration goes on, it identifies these nodes prefer this one, and these nodes prefer this one. Okay. Of course, there are some other similarity across the clusters. So that's the general idea. So you give me a n by n matrix. You're given an n by n matrix. These matrix entries are similarity. Tell me I and j how similar they are, and you just use this similarity matrix running this message parsing algorithm or affinity propagation algorithm to get the exemplars out. So we'll see the mathematical formulation. So first we can ask what are the similarity matrices in our problem. Well, we already have them. It's because we have this similarity defined between the labels, and this can be extended to be the similarity between nodes, because if we know the ion identity of the nodes, just use a dictionary lookup, we'll know there's no similarity between nodes. Okay, and the adjacency matrix of this weighted graph provide another similarity matrix along the edge dimension. So right, I have 2 similarity matrices, and we do clustering using these two similarity matrices, but jointly we have a constraint, the big constraint I stated here. So that's why it's called joint affinity propagation. So the output of the range will be look like this. The affinity propagation, if you just do clustering along, say, along the edges. Okay, each clustering, we have two clustering on the edges, clustering along the nodes. Each clustering will give you a binary matrix. How to interpret this? Suppose I label the nodes, I cannot say label here, I should say the number. I just give it this called 1, this called 2, 3, I call give the numbers to these nodes. Then you have a 6 by 6 binary matrix. If you add each row, for example, this row means the first vertex prefer itself to be the exemplar. And this node, the second node, prefer the first node to be exemplar. So this ith row jth column means ith object prefers the jth object to be its exemplar. And this corresponds to the edge cluster. For example, if you look at this, the first column, 1, 2, 3, all prefer this one to be the exemplar. So this is an edge cluster. And similarly, the fifth column saying 4, 5, 6, all prefer this one to be the edge cluster. Then I have two clusters. It's like I cut here, it's a one subgraph, another subgraph. And this matrix is the node clustering result. It tells me that if you look at the color 1 and 4, you look at the fourth column. This is the first node prefers the fourth node to be the node exemplar, and the fourth node prefers itself. And you look at another 2 and 5, 3 and 6. So this is the output. We learn the binary indicator variables for clustering assignments. Okay, so affinity propagation, we try to learn the binary variables is 0, 1, so it's integer programming, and formulate the example-based clustering as a constraint IP problem. This constraint is not the big constraint I'm saying. This constraint is just to constraint the binary indicator variables to be indicator variables of meaningful cluster assignments. For example, I can only be assigned to one cluster, so only in each row, if you look at the row, in each row, only one element can be 1. So that's the original constraint in affinity propagation. And to solve this IP problem with message parsing. The IP problem, if we state it, is like given n by n similarity matrix, Sij, and we maximize this linear program, this linear function, linear program, where Cij a binary, and this constraint is just saying if somebody I choose J as its exemplar, the J must choose itself as exemplar. And this constraint I label as II, saying there's only one element, and only one. There should be one and only one element to be 1 in the row, in one row. Okay. So this could be solved by message parsing. We just change these constraints to penalty functions, which are treated as vectors in the vector graph. But this is from graphical model. You have these variables, Cij, you want to learn as the indicator variables. You have these vectors. This is constraint the ith row. This is constraint the jth column. So it's a lot of constraints. And this Sij is saying if Cij is equal to 1, what will be your gain, the similarity from assigning I to j. It's related. This is the objective function. This is a penalty function from the constraints and pass the messages. Use max product message passing algorithm. And in the graph model for the joint affinity propagation, we have two parts, right? Suppose this is if you look at the graph here, okay? We just have this twin here. This part represents, if you only look at this part, this represents the edge clustering. If you look at this part, this represents the node clustering. And this HJK is really the big constraint. I'm saying, if I is assigned to the jth edge cluster, so HJK has two indices. J refers to the edge cluster example. K refers to the node cluster example. So if I is assigned to the jth edge cluster and is also assigned to the kth node cluster, then can be node by other L, which is not equal to I, is also assigned to the jth edge cluster and the kth node cluster. So you need to state out this as a penalty function, and it define this nothing but also the potential function in this graphical model, and do the massive passing moments on this. Okay, so that's the high level of the mathematical description, and let's see some demos of this. So this is the example used along the presentation. And this is the given initial structure. We have the weights on this. In my experiments, I fixed these three edges and these three edges to have weight 1, and all the rest connections are sampled from a normal standard a normal distribution with standard deviation 0.2 and take the absolute value. So I put all the weights to be positive. And let's see as time goes on, how the algorithm is going to learn these two subgraphs as well as alignments. So after 3 iterations, it only learned this edge cluster and then gets in the node alignments. It's already correct, but it can change the connection, what examples you need. So in the end, it tells me that if I use this pink to mean the edge clustering, this cyan dashed line to mean the node clustering, it tells me that these two nodes prefer this red node to be their edge examples, and these two nodes prefer this green node to be their edge examples, and this cyan dash lines tells me they prefer to be aligned this way. Let's see another example. The connection the number of connections is lesser than the previous example, but the weights here in all the edges, consider these links to be the things we want to cut. All the weights are 1, and how are you going to learn this? It's now progressing very quickly to the correct solution, and it's because the massive parsing algorithm is non-trivial to implement. We have a lot of scheduling problems in it. So in the end, I still learn this intended structure. And this tetrahedron example, the progress is very, very slow. You use 200 iterations to get to the correct answer. Okay. Then we have this subgraph, and the nodes align. Okay. So some discussions. There is difference with spectral clustering because we only consider the edge to be one example being selected. We don't discard the edges of nodes, not of other nodes. And there is another thing we need to consider because object function involves edge and node clustering. So how are we going to weight these two parts? Which one should be more important is also being explored. And how do you implement the master parsing algorithm so that it can scale to a very large graph? And the two big questions for us is how are we going to evaluate learned building blocks? And how are we going to use the learned building blocks for crystal structure prediction? How are we going to pack them together? Find the crystal structure we predict. So if you can help with these two questions, that would be very good for us. Yeah. Thanks.
Thank you. Any questions?
Question? We have a few more minutes. If there are any questions from folks that have connected from a distance, Mike, can they just use their microphone now?
Be better.
If they just did through the chat room?
Yeah.
Okay, so if you have a question, you're at one of our satellite.
Oh yes, they could unmute there.
Okay. Just unmute your microphone and you can speak through our audio here. Okay. Any other questions here in the room?
I don't think so my background's not in computer science.
Oh, it's fine.
Sorry, so do you go back to when you were given the examples of the models that you were doing? These, yes.
Oh,
so
okay.
some took, you mentioned the last one took 200 iterations.
This one. Right.
So how do you know, I mean, for the other ones, what if you did more iterations, what if, you know what I'm saying, how do you know when to stop, how do you know that's
okay,
the
right,
number
that's a
iteration?
good question.
So
This question, we're still trying to solve it. In general, the message parsing algorithm is no guarantee to converge. It's because it's because they're trying to use this to solve an NP-hard problem, and there is no guarantee it can converge to an optimal solution, even no convergence most of the times. So for our problem, we are trying to use some heuristics to enhance the convergence of algorithm. For example, because we're clustering node according to node, according to the edges. So one thing you can think that how about we first try to do some iterations on the node part, and we'll fix the node clustering results, and then we do the rest part, the edge clustering. Because we found that if we do each clustering individually, we can converge very quickly to the intended solution. But if we put them together, there is oscillation of the messages passed. So we're trying to work out the way, say, how many iterations I'm going to do on the node part, and to fix that, then the node alignment will be used as the clue for the edge clustering to cut the pieces, so to respect the node alignment.
and each iteration, that would depend on each material you're doing, correct? It wouldn't be uniform across? Or
generally, if we can work out, it could be depending on the graph structure and the similarity matrix.
The structure, yeah.
Right, but let's see whether we can come up with the algorithm that is invariant to the graph similarity matrix. Yeah, but that's I admit that's a big problem. Yeah. Well, another way to go this is that we just do not hope algorithm to be convergent, but we save the objective function value along the path. So this way we save a lot of intermediate results, and then we pick the one that achieves the best objective value, objective function value. So this is more like using message parsing as a searching algorithm rather than just give me the final solution.
Okay.
Right.
Yeah.